Hello everyone and welcome to our presentation. We are Group B of the class of Python 2. We will introduce in this session our presentation for the usage of the FairDetect class that was provided to us by Professor Manuel and the improvements that we implemented to that particular class and implementing it against a synthetic credit card dataset, as well as comparing our class with another class that my colleague Christian will present later on in this presentation, plus saving the results in SQLite, which my colleague Dominic will also present in this presentation. Now, what is FairDetect as a class? FairDetect is a framework that allows us to detect and understand biases in machine learning. It's based on three major fairness metrics, which are representation, ability, and performance. Now, for the sake of this presentation, we're going to jump between two notebooks. First notebook is actually where our library is written or is scripted, and which was later on uploaded into PyPy and GitHub, and then further installed in this particular notebook that you see in front of us, which allows users to implement our methods in any data set that they wish to examine or check for biases. Now, within this presentation, I will be jumping back and forth between the actual library and the improvements that we did to the FairDetect class, and then showing you how does that look like as an output. So, first improvement and in general improvements are either about adding additional methods that are very helpful or around user experience. Now, in terms of user experience, first improvement that we wanted to talk about is allowing our users, first of all, to select the target variable from the data frame that we're talking about. So selecting the target column, we want to make sure that the user is selecting a binary target, because this is at the end of the day, this is our data set and we're expecting something of logistic regression. So selecting the target column and this particular method that is called check for targets. First of all, it will make sure that what you selected is a target variable, and if it's not, it will tell you that please select the target variable. If it is selected correctly, it will actually tell you that you chose wisely. And how does that look like? It will look something like this. So in this particular example, and out of convenience in our data frame, the target is actually called target, and it tells you that you chose wisely. If I selected income, which is kind of a continuous variable, it will reject it. Going back to improvement number two. In improvement number two, as you can see, in every single method within our library, we added docstrings to explain to the user what is the usage of this method and what it is expected to return in terms of value. Now, in terms of improvement number three, we introduced a new method which is called disparate impact. So the disparate impact actually will help our users in seeing the ratio of favored or unfavored groups within our data set. And to show you how it actually looks like, this is an example, and we additionally provided some benchmarking or some ratio that will help you understand what is a good ratio. So anything between 80 and 90% is actually indicating a mild impact violation, but we can never have basically a ratio of 1. So very unlikely, but if it does, it displays perfect equality. Now, on the improvement number 4, So if we're talking about user experience in particular, these are the biggest changes that we're going to discuss now in terms of user experience, which actually allows you to check for or actually create your own labels. So in binary values, zeros and ones, when we're talking about a sensitive variable such as let's say Hispanic or non-Hispanic, for that particular case, if I'm using zero and ones and I'm the whole time, users might get confused and forget what is the zero and what does the one represent. It additionally allows you to use the description of zero and one. So if I select Hispanic and non-Hispanic, it will display in every single visual, instead of displaying a legend of zero and one, it displays a legend of Hispanic and non-Hispanic. In addition to the sensitive label, there's the target. We selected the target previously, we checked it was binary, but now it's time to name it. A 0 or 1, what do I call it? Approved or denied? And we will see these directly in the notebook, so you get a feel of what it is actually doing. So for example here, the representation of the sensitive variables. Here we're asking the users to select for group 0. So the group was the sensitive variable. For 0, we called it Hispanic. For group 1, we call them non-Hispanic. Now for the target names, we use denied and approved, denied being 0 and 1 being approved. And this is how it looks like. So for the rows, the target names, and for the columns is the sensitive variable, to just actually look at the true positive disparity, false positive, true negative, and false negative. And you can see that this result, so rejecting the null hypothesis, is actually bolded out so that to attract attention towards this output. And in addition, this actually looks better than having zeros and ones on each side of the table. In addition to all of these adjustments to user experience, we introduced as we have mentioned, quality control methods towards the checking the target if it's binary or non-binary. This is something also that we can consider as part of user experience. One of the improvements we did was actually directly on our Jupyter notebook, but actually required some adjustment in our library as well to make it happen, which initially the FairDetect class was only representing one of the class members. So let's just say Hispanic and non-Hispanic. It's giving the model importance for one of the class members. What we did here is we created an iteration which helps us compare the same metrics for both class members. Improvement number 6, which is actually related towards storing our data in SQLite. And that is something that my colleague Dominic will talk more about, but just because it is an improvement to our class, it's actually storing the key performance metrics or anything that measures biases in our SQLite. So from true predicted true positive rate, false positive rate, true negative and false negative, and disparate impact ratios are time and date stamped and stored in SQLite. Now, of course, with all these improvements, there is a trade-off. We improve the quality, we improve the user experience, and the checks and balances for this class. But in comparison, loading the libraries and the functions before these improvements took around 2.7 seconds, and loading the libraries and functions after these improvements took around 4.8 seconds. In isolation, using the FairDetect class without any libraries loading used to take 0.5 seconds to load before any improvements, and after the improvements, it took around 0.7. Now, the variance isn't that high between before and after in terms of time consumed, but just imagine how many improvements we will experience throughout this cycle, how many more contributions we can expect to make to our FairDetect class. So that will delay it even further and delay our model. And with that note, it concludes our first section, and I will hand over to my colleague to resume.
For the comparison of FairDetect, we have chosen AEquitas, which is another open source bias detection toolkit. Both toolkits have been used on the outcome of an XGBoost classification algorithm applied to the synthetic credit card approval dataset. After going through each of them individually, we will highlight some of the differences. When using FairDetect, the first element is to identify the sensitive variable. In our case, group, a binary variable, which for readability we have identified as 0 for Hispanic and 1 for non-Hispanic. The tool follows 3 steps: identify bias, feature importance, and disparate impact. Once created the object, the first step is to apply the method identify bias. This method shows the contingency table and the result of a chi-square test between subgroups. We see that the test detects significant relationship between group and target. This result is further analyzed through the ability disparities of each subgroup for 4 key metrics: TPR, FPR, TNR, and FNR. Despite the differences we see in the graph, the tool doesn't identify any significant disparity. The following metric produced is the difference in precision, which is called predictive parity, which again yields no significant disparity. The second step looks into the black box model using SHAP to interpret the feature importance. Looking at the most affected group, in our case Hispanics, with wrongly rejected credit card, the 00, we see on the left-hand side of the plot the feature ranking with no big significance or differences within the subgroups. And in the right-hand side, for the isolated Hispanic group incorrectly rejected, where despite the order of the features is the same, income has a much lower weight, while group and owning a house have bigger impact on the model result. Furthermore, the tool extracts a random data point and produces a waterfall graph with a combination of the variables. We see an individual for subgroup 0 with a high salary, but not enough to compensate the negative weight given to group or not having a car. Finally, the third step is the obtention of an overall fairness metric. The disparate impact between the privileged and unprivileged subgroup that receives the positive outcome. In our case, the result is 3 times. Moving to AEquitas, we have to say that this toolkit has also 3 steps, but has a more scientific approach. However, the first thing it requires is something or reformatting the dataset. We have to add the score and the label value at the left of the dataset and bin the variables. Then we can get the basic values and up to 11 metrics in a table format. We can identify, for instance, in the metrics an important false positive rate for high incomes up to 0.34. We can also see the metrics in a graphic format, and here it is the false negative rate for the high incomes that we have identified before. In a second step, we obtain the model disparities for each class and the significance with the bias method. We have set a 5% confidence. Disparities are calculated against a reference class. We see that they have 1 in all the variables. As opposed to FairDetect, AEquitas finds significance in group. We see the true here, but also in high income, owning a house, and owning a car. The tool has an intuitive visualization tool for these comparisons. Here, for instance, for children, where we see all gray, no disparity, but for the group, we see a disparity above 3 in this graph. We can also see the overall fairness with the method fairness. We have chosen predictive positive rate disparity. In green, what is considered fair, and in red, we see the disparities detected and also matched to a scale. Here, we see not owning a car, high income, Hispanic, and none or above 3 children being unfair. But we can get the same result for other metrics, and precision, for instance, would be completely fair. The final step would be the parity test, for which, given a preset tolerance, the disparity tolerance method shows a visualization of selected metrics with a fail and pass method. We have to say that for a metric to be considered fair, it has to be blue for all the variables. Like precision, we have seen it before. The tool brings another visualization showing the scale, but variable by variable. We see some dots out of the tolerance we have set. Our conclusion after this exercise are that AEquitas may be more scientific and comprehensive. It provides up to 11 metrics, both in table and graphic formats, and hence it seems to target more policymakers and public initiatives. On the other hand, AEquitas requires more involvement, but at the same time, it seems more sensitive. Nevertheless, it needs reformatting of the data and binning of the variables, what might have also affected the comparison carried out.
Okay, the next part is about saving our KPIs, the p-values, into SQL. We're using, as a bridge between Python and SQL, the SQL Alchemy. The first step is to importing the package with the methods here. Then we are creating the class in order to store the p-values. First thing always in order to store them is to instantiate the method with the p-values of true positive rate and so on. And then we have the method for the dynamic data entry with the doc strings explaining what are each of the p-values. Here in the query, we are having the comment to insert into the database the p-values together with a random ID between 1000 and 10,000, and then to create the connection to the database. This line of code is creating a new database called credit card approval. If it has not been already created, it would be created new. If it's already there, nothing would happen. And here in YouTube Video Notebook, you would see this particular database that we have defined, where all of your p-values would be stored. And here we are defining the table, how it should look like. We have first an ID, which is an integer, the random integer, then a date, which is the current date, within the time. Then all of the p-values, which are defined as data type floats with a default value. Then we would have also the metadata created. And here is the connection. And the first thing we are doing in order to check that our creation of the database was successful is we are printing the name of the table we are having in our database, which is p-values. So this is correct. And then we are printing of this particular table all of the columns, so ID, date, and the p-values and the impact. And then we are printing for each of the columns of this p-values table the metadata. So you would see whatever we've been defined here before would be printed out here as well. Then we would have here the part about storing actually the p-values. So we have first created the table. Now we are storing the p-values. We're defining what should be in the table. And we are saying here this should be inserted now via this method that we have been defining here above. And after it has been inserted, we also want to check that it was successful. So what we're doing is an SQL query, and the SQL query would be that we are connecting to the database and selecting all, fetch all, it's called, with SQL Alchemy. And we would select the head of our data frame. And as you can see here, the ID is random. This is the current date, so whenever it has been saved, and those would be always the p-values and the disparate impact.
For the PyPy part, the first step is to check if we have installed the wheel and twine packages. Wheel is used to create the WH files, and twine is used to load your package to PyPy. If not, you must install them prior to uploading your package. To check this, we use the piplist command. As you see here, we have these two packages already installed, here and here. After that, you must locate your package path and inside it, create a setup.py file. This file must contain information about our package and requirements. The setup keywords are package name, package version. It is important to update the version number after making a change. It is mandatory. Description, URL, author information, license, packages, its location in your computer, and user requests. This is important because during pip install, the system check if these requirements are covered. In our case, check if Dalex is already installed, and if not, it will show an error and stop the installation. After that, we can create the source distribution file and the WHL file. At this point, we have all things ready to upload our package on PyPy. We use this command two times, one for tr.js and the other one to WHL file. As you see on PyPy, here is our package uploaded. To finish, you can copy this command and paste it in your Python environment to install our package. Here it is. So, thank you everyone.